G'day Space Cadets, and welcome to this deep dive into Lagrange points. In this video, we're going to discuss the physics and stability of each Lagrange point in detail. We will develop a physical understanding using the fundamental and intuitive building blocks of acceleration, force, velocity, and animations that took a painfully long time to render. Only as a final step will we introduce the energy potential surface. If you've watched other videos on the Lagrange points, you've no doubt seen one of these surfaces before. The energy potential surface is a very useful mathematical tool, but in my opinion, it can't be understood intuitively very well without a solid understanding of the fundamental aspects first. This video is a long one, so go get your coffee, beer, or extracurriculars and let's get started. I promise there won't be too many equations, but we do need to cover some basic orbital mechanics and review the centrifugal and Coriolis forces to properly understand the Lagrange points. I've included timestamps in this video so you can skip particular topics that you may already be familiar with. I'm going to use the words force and acceleration interchangeably in this video. In orbital mechanics, we're rarely concerned with the actual gravitational forces, so we usually divide both sides of the equations by the mass of the spacecraft and just work with accelerations. Alright, time for some maths. The orbital period of a small body, like a planet, on a circular orbit around a large body, like the Sun, can be calculated with this equation, where t is the orbital period, r is the radius of the smaller body's circular orbit, g is the gravitational constant, and m1 is the mass of the large body. Lagrange points only really exist when the secondary body is in a near circular orbit about the main body, so we will restrict ourselves to the circular case. As g is constant, often g and m1 are lumped together into what's called the gravitational parameter of each celestial body. A simpler way of stating this equation is that the orbital period depends on the orbital radius divided by the gravitational strength of the primary body. If we keep the same primary body and increase the orbital radius, then the orbital period must also increase. Conversely, if we keep the same primary body and decrease the orbital radius, the orbital period must also decrease. We can summarize this as objects in larger orbits rotate slower, and objects in smaller orbits rotate faster. Let's have a look at a map of the Lagrange points in the Sun-Earth system now. Conversely to what we have just discussed, all of the Lagrange points are at different orbital radii than the Earth, yet they all have the same orbital period. Let's return to our previous equation to understand how this is possible. The orbital period is fixed, so the only remaining variable that we can play with to alter the orbital radius is the gravitational parameter. This is the well-kept secret of the Lagrange points. Each point has a slightly different effective gravitational parameter. When we analyze the orbit of a planet around a star, the mass of the planet is usually much smaller than the star, and so we can ignore it. However, when we are analyzing Lagrange points, we are considering how a tiny spacecraft behaves in the presence of two celestial bodies which are both much bigger than the spacecraft, and so we must consider the gravitational effect of both the bodies. The interaction of the gravitational fields of the primary body and the secondary body means that there is no longer one constant gravitational parameter. In fact, it is constantly varying throughout 3D space. The Lagrange points are particular locations in space where the interaction of the two gravitational fields make it possible for a spacecraft to orbit the primary body with a kind of unnatural orbital period for the radius of its orbit. The Earth is on an almost circular solar orbit, and so it has a constant angular velocity around the Sun. The fact that its orbit is circular also tells us that the centripetal acceleration required for circular motion around the Sun is exactly provided by the Sun's gravitational attraction. Let's now consider a spacecraft at Lagrange point 1, between the Earth and the Sun. Since the spacecraft is closer in than the Earth, normally it would orbit faster than the Earth. However, at L1, Earth's gravity is pulling in the opposite direction to the Sun's gravity, and acts to artificially weaken the Sun's gravity. This artificial weakening allows the spacecraft to still orbit the Sun with a period of 1 Earth year, even though it's closer to the Sun. This effect is the same as reducing the gravitational parameter. It's important to note that the Earth's gravity isn't equal and opposite to the Sun's gravity and cancelling it out or anything like that. Rather, L1 is just an interesting point in space where the combination of the Sun's gravity and Earth's gravity make it possible for an object to orbit the Sun on a circular orbit with a period of 1 Earth year, while having an orbital radius that is different to Earth's. In the Earth-Sun system, the L1 point occurs at a distance of approximately 1.5 million kilometers closer to the Sun than the Earth, which orbits the Sun at a distance of about 150 million kilometers. If the Earth were to suddenly disappear, a spacecraft sitting at L1 would experience the Sun's full gravity. It would be moving too slowly to stay on a circular orbit with this increased gravity. Moving too slowly to stay on a circular orbit is basically the definition of the apoapsis of an elliptical orbit, and so the spacecraft would enter an elliptical orbit about the Sun and start falling back towards its solar periapsis. The period of this new orbit would be less than 1 Earth year. Let's move on to L2, where we basically have the opposite situation to L1. The gravitational attraction of the Sun and the Earth are both pulling in the same direction this time, artificially strengthening the Sun's gravity and allowing a spacecraft to orbit further out than the Earth while still maintaining a solar orbital period of 1 Earth year. This effect is the same as increasing the gravitational parameter. In the Earth-Sun system, L2 occurs at a distance of approximately 1.5 million kilometers further out than the Earth. If the Earth were to suddenly disappear, a spacecraft sitting at L2 would experience a reduced gravitational attraction. It would be moving too fast to stay on a circular orbit with this reduced gravity. Moving too fast to stay on a circular orbit is basically the definition of the periapsis of an elliptical orbit, and so the spacecraft would start drifting upwards towards its solar apoapsis on a new elliptical orbit. The period of this new orbit would be greater than 1 Earth year. Now L3. L3 is basically a less extreme version of L2. Both the Sun and the Earth pull in the same direction and the spacecraft experiences an artificially higher gravitational effect. However, because the Earth is so much farther away from L3 than L2, the additional gravitational attraction from Earth is much smaller. A spacecraft at L3 in the Earth-Sun system would orbit the Sun on a circular orbit only about 260 kilometers further out than Earth's orbit. Similarly to the situation at L2, if Earth were to suddenly disappear, a spacecraft at L3 would enter an elliptical orbit with a period slightly greater than 1 Earth year. Moving on to L4 and 5. These guys are a mirror image of each other, so we'll just consider L4. The diagram here is a bit more complicated than for the previous points, but the logic is still exactly the same. When discussing L4 and L5, it's important to note that the Earth isn't truly orbiting the Sun, rather the Sun and the Earth are both orbiting their combined centre of mass, which we call the barycenter. For the Earth-Sun system, this point is still well inside the Sun due to the much larger mass of the Sun. In fact, the Earth-Sun barycenter is only about 500 kilometers from the centre of the Sun. At L4 and 5, the spacecraft sits at a point that is equally distant from both the Sun and the Earth, on the tip of an equilateral triangle. As always, the spacecraft experiences gravitational attractions from both the Sun and the Earth. When these gravitational attractions are combined, they form a slightly larger acceleration vector that points towards the Earth-Sun barycenter. Just like L2 and 3, we have a situation where the spacecraft is experiencing an amplified gravitational attraction, and so its circular orbit will be approximately 600 kilometers further from the barycenter than Earth's orbit. Again, just like at L2 and 3, if the Earth were to suddenly disappear, a spacecraft at L4 or L5 would enter an elliptical orbit and drift higher. The period of this new orbit would be slightly greater than 1 Earth year. Now we understand how the Lagrange points allow spacecraft to exploit the gravity of two different celestial bodies in order to orbit the primary body in ways that would not be possible with the primary body alone. In an ideal world, spacecraft could happily stay at any of the 5 Lagrange points indefinitely. However, for better or worse, we live in the real world where planetary orbits are not exactly circular and a variety of orbital disturbances exist. In order to make practical use of the Lagrange points, we also need to understand what happens to spacecraft when they are perturbed away from these ideal locations. In order to intuitively understand the stability of the Lagrange points, we're going to switch to a rotating reference frame, which means it's time for a brief recap of every high school physics teacher's worst nightmare: fictitious forces. When we say fictitious, what we really mean is that these forces can't be measured directly. For example, we can't use an accelerometer to measure the centrifugal or Coriolis forces. The reason for this is that the centrifugal and Coriolis forces only appear when we are looking at a problem in a rotating reference frame, while physical processes which we can directly measure occur in a stationary, non-rotating reference frame, which we call the inertial reference frame. You might ask, why bother using a non-physical reference frame with fictitious forces that we can't directly measure? The answer is that kind of counterintuitively, problems with complex rotational dynamics can be understood more easily via these fictitious forces. As we will see later, when working in the inertial frame, we only have the gravitational acceleration vector to work with. As both its magnitude and direction vary throughout space in the three-body problem, spacecraft motion can appear chaotic and be hard to interpret using this one acceleration vector alone. When we swap to a rotating reference frame, this one acceleration vector can be broken down into several components, both physical and fictitious, which each tell a small part of the whole story and can make a complex trajectory much more understandable. Let's start by reviewing the centrifugal force. In an inertial reference frame, the gravitational attraction between a spacecraft and the central planet provides the centripetal acceleration required for a circular orbit. It's important to note that in order for a centripetal acceleration to exist, a tangential velocity must also exist. Let's now consider a rotating reference frame that rotates with the same angular velocity as the spacecraft. The gravitational acceleration vector still exists in the rotating reference frame, as the gravitational acceleration only depends on position. However, in the rotating reference frame, the spacecraft appears to have no velocity, and so a centripetal force can't exist. Since the only acceleration acting is gravity, it appears that the spacecraft should just fall towards the planet. But we know this isn't what happens in reality. To make the rotating reference frame situation behave like reality, we need to add in a centrifugal acceleration to stop the spacecraft falling into the planet. In the case of a circular orbit, the centrifugal acceleration is equal and opposite to the centripetal acceleration provided by gravity in the inertial reference frame. In the case of non-circular orbits, the centrifugal force will not always be equal to the gravitational acceleration. Now we're ready to move on to the Coriolis acceleration. In the rotating reference frame, at first glance it looks like an astronaut aboard our spaceship could simply throw something towards the Earth and it would continue downwards until it hit the surface. However, there are plenty of examples of CubeSats being deployed from the ISS either by astronauts tossing them or via mechanical ejection, and none of them directly descended downwards and crashed into the Earth. We need to keep in mind that in reality both the CubeSat and ISS are undergoing high-speed circular motion, even if we can't see it in the rotating reference frame. As any KSP player would know, if the CubeSat is ejected radially towards the centre of the Earth, it would enter an elliptical orbit with an apoapsis slightly higher than the ISS's orbit, and a periapsis slightly lower than the ISS's orbit. The two objects would keep the same orbital period and have regular, close approaches twice in orbit. Let's see how this looks in the rotating reference frame. When the CubeSat's altitude is below the ISS, it picks up a higher speed and angular velocity, and therefore the CubeSat rotates faster about the Earth. It gets ahead of the ISS in the rotating frame. Conversely, when the CubeSat is above the ISS, it slows down and the ISS catches up and overtakes it. From the point of view of an astronaut on the ISS, who naturally experiences this situation in a rotating reference frame, it appears that the CubeSat is almost orbiting the ISS. To explain this peculiar motion in the rotating reference frame, we introduce the fictitious Coriolis force. The Coriolis force acts perpendicular to any relative velocity in the rotating reference frame. Similarly to a centripetal force, it acts to create circular motion but within the rotating reference frame. Hopefully, you can understand now that even if these forces are fictitious and can't be measured directly, they can still represent physically meaningful phenomena and are a useful way to understand motion from the point of view of a rotating observer, such as an astronaut on a spacecraft orbiting Earth. Let's quickly summarize the key forces we've discussed. Firstly, we have the gravitational acceleration, which exists in both the inertial and rotating frames, and it depends only on the spacecraft position within the frame. Secondly, we have the centrifugal acceleration, which only exists in the rotating reference frame. The centrifugal acceleration depends on both the position of the spacecraft in the rotating frame and the angular velocity of the rotating frame. Finally, we have the Coriolis acceleration. The Coriolis acceleration only exists in the rotating frame, and it depends on the velocity of the spacecraft with respect to the rotating frame, as well as the angular velocity of the rotating frame. Okay, now we're ready to start analysing the stability of the Lagrange points. We're going to do this by modelling what happens when a spacecraft sitting right on a Lagrange point is disturbed. This disturbance could be due to many things: solar radiation pressure, gravity from other planets, inaccurate thruster firings, even collisions with other objects. It's important to understand that the three-body problem is chaotic, which means that a small change in the initial conditions can create wildly different results. Unfortunately, I don't have time this afternoon to simulate an infinite number of disturbances and their outcomes, so we'll have to make do with just a few examples. In these examples, I've used the Sun-Earth system, but upgraded to a super-Earth with 1,000 times the real mass of Earth so that the Lagrange points are more spread out and easier to see. All of the upcoming animations are rendered at high frame rates so that you can replay them more slowly if you like. Please note that the scaling of the acceleration vectors changes from case to case in the following animations in order to effectively show the relative sizes of the gravitational, centrifugal, and Coriolis accelerations in each situation. Let's start our stability analysis at L4. We're observing a spacecraft sitting precisely on L4 from a rotating reference frame which is turning about the Sun with the same angular speed as Earth. In this reference frame, the spacecraft appears stationary. If left undisturbed in a perfect world, it would sit there forever. Let's disturb it by giving a small velocity component towards the Sun and see what happens. We see the spacecraft depart from L4 and start travelling in some funky looking loops. Don't forget, we're in a rotating reference frame, so some surprising behaviour is to be expected. To better understand what's happening, let's break down the accelerations acting on the spacecraft in the rotating frame. We have the gravitational acceleration vector due to the combined effect of the Sun and the Earth in blue, the centrifugal acceleration in red, the Coriolis acceleration in pink, and in yellow we have the resultant acceleration, which is the sum of the gravitational, centrifugal, and Coriolis effects. Initially, the gravitational acceleration and the centrifugal acceleration are balanced, and so the spacecraft could have remained at L4 indefinitely. However, we introduced a velocity perturbation towards the Sun, and so a Coriolis force appears perpendicular to this velocity. Let's re-watch the animation, but now with the accelerations included. As the spacecraft drifts inwards, the gravitational acceleration gets larger, which causes the spacecraft to orbit the Sun with a faster angular velocity, and it moves further away from the Earth. However, as the spacecraft picks up speed, the Coriolis force in the rotating frame increases. As the Coriolis force always acts perpendicular to velocity in the rotating frame, it encourages curved motion in the rotating reference frame. The Coriolis curving of the trajectory takes the spacecraft out beyond Earth's orbital radius to where gravity is weaker and where the spacecraft's orbital angular velocity becomes lower than Earth's. Earth then catches up a bit with the spacecraft. Let's now see how this peculiar motion appears in the inertial, non-rotating reference frame. Actually, it looks not so crazy after all. The spacecraft is simply on an elliptical orbit about the Sun, which is being continuously disturbed by the presence of Earth. The weird loops in the rotating reference frame are a result of the spacecraft rotating faster than Earth when it is inside Earth's orbital radius, and slower than Earth when it is outside Earth's orbital radius. To an observer on Earth, who would be observing the spacecraft's motion from Earth's rotating reference frame, the spacecraft kind of appears to be chaotically orbiting around the L4 point in space. Now it's time to detour briefly and introduce the energy potential surface. This is a fairly advanced topic, so feel free to skip ahead to the other Lagrange points if you like. The energy potential surface is a very useful tool for helping us to identify points in the rotating reference frame where an object can stay motionless because the forces on it are balanced, the Lagrange points in this case. This doesn't mean that an object at one of these points is motionless in reality. They are just motionless with respect to the rotating reference frame. In this situation, we are only concerned with the gravitational acceleration, the centrifugal acceleration, and the Coriolis acceleration. The Coriolis acceleration is only non-zero when the spacecraft has a non-zero velocity in the rotating reference frame. Since we're interested in stationary points in the rotating reference frame, we can set the velocity to zero and ignore the Coriolis acceleration. This leaves us with just the gravitational and centrifugal accelerations, which both only depend on the spacecraft's position in the rotating reference frame. The centrifugal acceleration term does also depend on the angular velocity of the rotating reference frame, but when studying Lagrange points, we assume a constant and fixed angular velocity. Effectively, what we're describing is the centrifugal acceleration required for a spacecraft to orbit the Sun with a period of 1 year at any given point in the Earth-Sun system. Currently, we're only working with accelerations, or forces if we were to multiply both sides of the equation by the spacecraft's mass. We could solve this problem to determine the location of the Lagrange points by setting the left-hand side equal to 0. This is equivalent to what we did earlier with the diagrams, just now we're using centrifugal instead of centripetal acceleration. If we want to be fancy, we can integrate this equation with respect to distance from the Sun. Integrating a force or an acceleration over a distance gives us energy in joules, or specific energy in joules per kilogram. These potential energies can be plotted to provide a powerful illustration which graphically tells us immediately where the Lagrange points are. Recall that we could calculate the Lagrange points directly from the force balance by setting the left-hand side equal to 0. Since the force balance is the derivative of the energy potential, this is the same as saying that the Lagrange points will occur where the slope of the energy potential surface is 0. It's important to note that the numerical value of the potential energy surface is not 0 at the Lagrange points, only the gradient of the surface is equal to 0. In the regions where the gradient is not 0, one of the forces is greater than the other, and so motion will occur. Where the plot slopes inward, the gravitational attraction is too strong for a spacecraft to orbit the Sun on a circular orbit with a period of 1 year. A spacecraft which is stationary at such a sloped point in the rotating reference frame can only be stationary momentarily while it is at the apoapsis of an elliptical solar orbit. It will immediately start falling back towards its periapsis. Conversely, if the surface slopes outwards, the gravitational attraction at such a point is too weak for a spacecraft to orbit the Sun on a circular orbit with a period of 1 year. A spacecraft which is stationary at such a sloped point in the rotating reference frame can only be stationary there momentarily while it is at the periapsis of an elliptical orbit. it will immediately start drifting outwards, away from the Sun. The slope of the energy potential surface can tell us only the initial direction that the spacecraft will travel. Once it develops a non-zero velocity, the Coriolis force comes into effect and everything gets complicated. A very important thing to note about the energy potential surface is that it contains no information about motion or kinetic energy. A spacecraft with a non-zero velocity in the rotating reference frame will have a kinetic energy which can't be shown directly on the surface. Instead, the spacecraft will travel across the potential energy surface, constantly exchanging potential energy for kinetic energy and vice versa as it goes up and down the potential surface. Let's watch our L4 example and see what happens once motion occurs. Notice how the motion of the spacecraft is neatly confined to a kidney bean-shaped region in between select contour lines. If we left the simulation to run for a long time, the spacecraft would eventually sketch out a kidney bean contour corresponding to its exact potential energy level. This stable oscillating behavior is characteristic of the L4 and L5 points in a system where the secondary body is much smaller than the primary body. The slope in the energy potential surface is very gradual in this region, and so the relatively small Coriolis acceleration can keep the spacecraft stably bouncing around within these regions. If the second body becomes too big, the gradients in this region get steeper and the Coriolis force becomes insufficient to contain an object within the L4 and L5 regions, and then these Lagrange points also become unstable. If we have a look at some animations of the Trojan asteroids captured in the L4 and L5 points of the Sun-Jupiter system, we can see exactly this kind of semi-chaotic motion about the Lagrange points, but now in all three dimensions. Let's now move on to L1. As we discussed in the force diagram section, the net gravitational acceleration on a spacecraft at L1 is still dominated by the Sun's gravity, but it is weakened slightly by Earth's opposing gravitational pull. The net gravitational pull provides the centripetal acceleration, which makes the slower than normal orbit possible. In the rotating frame, the centripetal acceleration becomes centrifugal, and it exactly balances the gravitational acceleration at L1, and so an unperturbed spacecraft could remain there indefinitely. Let's perturb the spacecraft and see what happens. Once we get away from the artificially low gravity at L1, the spacecraft quickly develops high translational and angular velocities with respect to the rotating reference frame, which in turn creates high Coriolis accelerations. When we compare the crazy-looking motion in the rotating reference frame to the true motion in the inertial reference frame, we see again that the result is not so crazy after all. Once the spacecraft is disturbed from the artificially low gravity point at L1, it quickly falls into an elliptical solar orbit with a correspondingly lower radius now that it is experiencing the full gravitational attraction of the Sun. Earth continues to pull on the spacecraft and affect its trajectory, with stronger effects happening when the spacecraft passes close to Earth. When we look at the potential plot, we can clearly see that the spacecraft has fallen into the Sun's gravity well. As it falls closer to the Sun, it exchanges potential energy for kinetic energy and speeds up, and then the reverse happens as it climbs back up the gravity well. In this case, the spacecraft fell away from L1 and happened to fall directly into the Sun's gravity well. Let's zoom in on L1 to understand why. In this case, the spacecraft was perturbed in the negative y direction. This velocity created a Coriolis acceleration which pulled the spacecraft in the direction of the Sun, at which point the Sun's gravity quickly became the dominant acceleration and the spacecraft rapidly fell down the Sun's well. Let's see what happens if a similar perturbation was instead applied in the positive y direction. The direction of the perturbance velocity has been reversed, which also causes a reversal of the initial Coriolis acceleration. The spacecraft is now pulled in the direction of Earth, and Earth's gravity rapidly becomes the dominant acceleration. Let's zoom out again and inspect this new trajectory. The spacecraft initially falls into Earth's gravity well and spends a short amount of time there before escaping. Remember, the spacecraft started at L1, where it had just enough potential energy to escape Earth's gravity well through the low energy valley at L1, and so it won't remain in a stable orbit around the Earth forever. Once every now and then, its orbital trajectory around Earth aligns with the L1 point, and so it can escape. Just like our first case, the spacecraft eventually falls into the Sun's gravity well. However, this time it's on a totally different looking trajectory than the first time. It comes very close to Earth a couple of times, and on one pass, the spacecraft performs a gravity assist flyby of Earth, which flings the spacecraft into a higher solar orbit. This animation provides a very good insight into how planets clear their orbits of other objects. Just a couple of these flybys would be enough to throw any small object well clear of Earth's orbit into the path of the other planets, which would in turn throw these small objects around. These interactions are why we don't see multiple planets on the same orbit. It's simply not stable. When we look at L1 on the energy potential surface, we can see that the slope is downwards towards the Sun or the Earth along the x-axis, while it is upwards along the y-axis. This type of point is referred to as a saddle point because of its shape. The L1, 2 and 3 points have these saddle surface geometries, and they are inherently unstable as the Coriolis force can't easily keep objects in a stable orbit around these points. It is possible to maintain almost stable orbits around the L1, 2 and 3 points with careful planning and a small amount of propellant consumption. We will discuss Lagrange point orbits in a later video. Let's jump to L2 now. The situation at L2 is really not that different from L1, with the main difference being the initial conditions. Here the centrifugal force must balance the artificially strong gravitational pull caused by the attractions of the Sun and the Earth combining. If we give the spacecraft a certain perturbation in the negative y direction, the Coriolis acceleration and Earth's gravitational acceleration combine to pull the spacecraft into Earth's gravity well, where it remains for a brief period of time before escaping out the low-energy L1 valley into a solar orbit. The spacecraft basically performs two energy-depleting gravity assist flybys of Earth, which leave it in a low solar orbit. On the potential surface, we see the same kind of behaviour as before, an oscillation between slow motion at the top of the gravity well, when the spacecraft has lots of potential energy but not much kinetic energy, and fast motion deep in the gravity well, when the spacecraft has a lot of kinetic energy but not much potential energy. With a modified initial disturbance, we can also make the spacecraft depart L2 out the back door of Earth's gravity well. Without the artificially strong gravity of the combined Sun and super-Earth keeping the solar orbit low, the spacecraft enters a much higher orbit, and in the inertial frame we can see that the spacecraft is now just on a large elliptical orbit. At L3, the slopes are much less steep, and so we would expect to see slower and less chaotic motion. Let's have a look. If we perturb the spacecraft in the negative y direction, the Coriolis force pulls it outwards and it begins a kind of lumpy motion around towards L4 and Earth. However, before it actually reaches Earth, it turns around and oscillates back the other direction. On this second swing, however, the circumstances are just right that it can briefly enter Earth's gravity well and slip out the low-energy L2 corridor at the back and enter a higher solar orbit. What we see in the inertial frame, again, is that the spacecraft is simply travelling on elliptical orbits around the Sun, which are being constantly perturbed by the Earth. The eventual encounter with Earth provides a gravity assist, which slings the spacecraft out into a higher solar orbit. On the energy potential plot, we see the spacecraft bouncing around the appropriate energy contour until it reaches Earth and slips out the back. This brings us to the end of our tour of the Lagrange points. I hope this was educational and maybe even slightly enjoyable. This video was a bit of a marathon, so in the likely event that you found a mistake, please leave it in a comment below. Please also leave any other feedback or questions that you may have below. In future videos, we will discuss how to orbit the unstable Lagrange points and also extend the logic that we developed here to geostationary orbits in order to understand why most geo orbits are not stable. Until then, have a good one.